My name's Stephen Powley. I'm a mature student studying for a PhD at Coventry University. The broad theme of my research is automotive cybersecurity, and in particular, I'm looking at applications of model-based systems engineering and how they can benefit the engineering activity, the systems engineering activity, not only for the technology, but also for the infrastructure and the enterprises that are responsible for delivering and maintaining and operating vehicles throughout what is now a very long lifetime on the road. My talk today is about my research and multi-context modeling applied to ISO standards for automotive cybersecurity and safety. And this is a really key theme, the idea of cybersecurity and safety and how we might integrate or harmonize the activities around those. My talk is in two parts today. So first of all, I'll talk a little about the context of automotive cybersecurity and safety and focus in on the research questions that I'm looking at. Then I'll establish some goals around the classic systems engineering idea of building the right system right, and then take a bit of a more focused look at how I understood what the needs of the industry were in order to focus the scope of my study. I established some key practices in the context and established a focus area, which is harmonization of international standards from ISO. Having established that focus, I had to understand how I was going to facilitate such an activity, and that's how multi-context modeling was born, which I'm introducing today. And zooming out a little bit further, with the techniques established, I'm then going to take a look at how I've used those to model and map between some standards and the terms and the concepts and the relationships between them that we've established through that activity. And then finishing off with a look at some action research which has been conducted with the ISO Task Force for Harmonisation, which is a part of Working Group 11 in the ISO Subcommittee 32 for Automotive Engineering, Road Vehicle Engineering. So I'm going to talk a lot about context today. Context is really important so that we can understand the needs of all the stakeholders that might be involved. And a modern vehicle and the environment it operates in and that it's developed and created in is much broader than it used to be. And not only do we have the vehicle technology, which would be our classic focus, but we also need to think about the infrastructure that we'll need for the modern automobile and connections in particular to that infrastructure and the enterprise capabilities that we need to support this increased interconnectivity between vehicles and infrastructure. Every connection between a vehicle and the outside world provides an additional vector for a potential cyber attack. And this connectivity is really one of the key aspects that I'm going to be focusing on in terms of cybersecurity and safety. So there is no safety without security. But there are other aspects of cybersecurity that we're interested in, particularly in the standards context. We're interested in privacy, financial and operational losses as well. So my research question is, how can cooperating organizations ensure that vehicles remain safe and secure throughout their life cycle? To understand that, I established two research goals, which broadly break down as describing what enterprises must do and showing how to prove it's been done well. So to establish the first part of that, I conducted an interview study with several experts from around the industry, asking the question, which conditions in the enterprise enable connected vehicle security by design and default through the life cycle? I spoke to expert participants in roles ranging from dedicated automotive cybersecurity experts in industry and academia through more general systems engineering, people involved in automotive, to the people who recruit teams into automotive and provide the human resource infrastructure, as well as people representing government and policy and legal aspects. So it was a broad scope trying to understand the true context of the enterprise capability needed to deliver security by design and default. So when I talk about security by design and default, security by design is understood to be the system we've delivered is secure because we designed it in such a way that it was secure. But that doesn't necessarily mean that it's secure in operation. So if you think about buying a piece of technology that's secured by a password, when it arrives with you, it might encourage you to use a 5-character password, a 10-character password, a 15-character password, or no password at all. And so default is about that configuration that we need to think about when we deliver the product. And there's clearly some commercial conflict between making things secure and making things easy to use. So having asked people this question, we established some broad categories that their answers tended to group into, with a view to building a model of their needs. I'm only going to share a few of those today that are particularly relevant to the talk. But systems thinking, as you might expect, was a very common theme. But not only systems thinking around the technology on the vehicle, but regulatory and engineering challenges, thinking about how we can take a multidisciplinary approach that links safety and security together. And alongside that, collaboration was really important. So we can't develop a multidisciplinary or even a transdisciplinary approach without collaboration. So we need to collaborate and work together on the creation of these secure and safe by design products. We need to be able to collaborate beyond the boundaries of our own organization and understand not only what we need in our familiar environment, but in environments around the globe. So vehicles, by their very nature, are able to cross borders, and the requirements as they cross borders can change. And that's a very interesting challenge that we could do another whole PhD about. But we're not going to solve it in our own bubbles, so we have to collaborate. Regulations and standards was a recurring theme. The automotive industry is very standards and regulations driven, as you'd expect for a safety of life product. But again, we saw this emphasis on the global perspective and working together, and not only people working together, but standardization products that work together. People also said, very important, to get involved in standardization yourself. It's not just enough to wait for the standard to come out and try and comply. Things need to be very fast moving when it comes to cybersecurity. And if you get involved in the standardization process, not only can you influence the shape of the standard, but you get a much earlier picture of what's going to become that standard activity across the industry. And very importantly, due diligence. So coming to that secondary research question, how do we show it's been done well? Well, we need to build evidence-based trust, and model-based systems engineering, with its capability for providing a single source of truth and connecting knowledge across the businesses that are involved, is a very powerful technique for doing that and providing that rigor. And that, of course, needs to be accompanied by strong policies and procedures. If you put the perfect process in place, but you're not able to enforce that people actually follow that process, then it's not going to be valuable. I'm just now going to zoom out a little bit and look at the full collection of themes that emerge from this study. And I've grouped these around the 6 classic context setting questions of who, where, what, why, how, and when. And always, if you've followed Simon Sinek's talks over the years, the why question is always at the middle. And the themes that emerge that help us understand why are themes of knowledge and culture and communication. So these are not technology-centric aspects necessarily, that they're about people and what people know and how they communicate that. That needs to be backed up by that due diligence. And in a fast-moving, emerging discipline like automotive cybersecurity, there's a lack of knowledge. So we have to research and invest in research, both internally in our organisations and through supporting research in academia, through sponsoring PhDs and similar activities. So we can see how these cluster around the other questions now. So the when are we going to do all this? Well, in the automotive industry, that is generally driven by the regulations and standards. And for road vehicle cybersecurity, yeah, that time is now. The legislation's there, the standard is there. Yeah, over-the-air updates is coming. That should be released in the first part of next year, and regulations R155 and R156 that cover road vehicle cybersecurity risk management and over-the-air updates, respectively, have been established and are in force for the UNECE signatory countries. So who needs to do this? Well, there's not enough people out there. We need to develop talent, and we need to put the structure in place to make the most of that talent and bring about some really quite fundamental changes in the industry. And we're not going to do that without collaborating, and we're not going to do that without providing the resources that people need. And only when we've got the whole of the rest of that picture should we think about how. And the big, broad umbrella how is about that systems thinking and thinking beyond traditional silos. And only right at the end should we really be thinking about the tools and techniques. So just to summarize all that, here's my guide in a slide for automotive cybersecurity and the key practices that you should be developing in your organization. You need to develop that talent and expertise internally and externally through collaboration. Don't just wait for the standard. Get involved in making the standard. Take a systems approach that bridges those silos, and make sure you've got expertise in security everywhere in the organization. Develop a security culture and make sure that responsibility for security is everywhere and everybody's. And to enable that, it's really central that you get your board on board. Yeah, this is not going to be a cheap undertaking. It's going to require a lot of painful organizational change, perhaps. So you've got to have buy-in from the top, both metaphorically and with cash on the table to pay for all of the advanced capabilities that you're going to have to develop. So my focus, I looked at all of this and thought, well, where's the key problem that I can help to solve within the scope of my PhD? And I looked at this complex system of systems, realised it's not business as usual. We've got unprecedented complexity. We need to think about people, vehicles and infrastructure. And the only real tool available to do that is model-based systems engineering. Now, there was a focus in the voice of the customer survey that I did, and it said, let's think about standards. Everything is led by standards in the automotive industry, but we need to bridge those gaps between standards and potentially harmonize and find value-adding synergy between these key documents. So the standards that I focused in on were ISO 21434, which is Road Vehicle Cybersecurity Engineering, released last year, and implementing UN Regulation 155, and Road Vehicle Functional Safety, ISO 26262, which is perhaps more familiar. That's been around in one form or another for a decade now, and that focuses on functional safety. And there is a lot of overlap between the two, but it was very difficult to see how we might achieve better, closer alignment between those standards in the future. And of course, thinking about a systems engineering approach is very important to look at how this might relate to our old favourite ISO 15288 for system and lifecycle processes. So what's the status quo in modelling? Well, generally, models only capture systems at a single level of abstraction and in a single context. So that might be a security context or a safety context or an electrical vehicle architecture context. Now, clearly, we understand that there are linkages between these two, but until now, it's been quite difficult to integrate all of that into a single integrating model. Of course, there's advantages to keeping things separate. You can conform to those traditional silos. It makes model control simpler, and it keeps concerns separate, a very important idea. And it lets people in the different disciplines do the configuration management at the level of detail that works for them. But there's a problem with this in that only focusing on one context per model makes it very difficult to share parts of that model effectively. It makes it harder to understand the emergent properties, both the desirable and the undesirable. And it's definitely more difficult to avoid the unintended consequences. So we need to think about how can we take advantage of those desirable emergent properties, and by constructing viewpoints that address non-functional concerns such as security and safety, resilience, and bridge those gaps across the models with multifunctional viewpoints. And finally, a very common theme in systems engineering conversations is about terminology and definitions. And the reason for that is because terminology and definitions are used to refer to and explain the concepts that we're working with. And if we don't all understand concepts in the same way, it's very difficult to communicate about them, and that's what leads to problems down the line. So multi-context modeling is an approach to solving those issues. And in particular, we're looking at challenges where the same term means multiple things, or we've got different terms to mean different things. But also looking at the conceptual modeling, people have different ways of viewing the world, and their fundamental worldviews can conflict. And that's why it's useful to develop conceptual models, so models of concepts and the relationships between them, also known as ontologies. And these ways of viewing the world can be understood through foundational ontologies and developing an understanding of what are known as ontological commitments. So to bridge between the contexts, we need models that accommodate all of those 3 points there. And if we do that, then we've started to lay the groundwork for digital transformation initiatives, which are a frequent target of enterprises, but have traditionally proved very difficult to deliver in practice. And if we have these integrating overarching models, then that gives us a good basis to make successful digital transformation. So why standards? Well, it's important to get involved. It's not that difficult to become a participant in the standards making process, but it is time consuming. To participate, you just need to get in touch with your national standards body. So that's the British Standards Institution in the UK, for example, or the DIN, Deutsche Institut für Normung in Germany, and so forth. It's a really valuable activity. And one of the things that you might not have thought about when weighing up the pros and cons of getting involved is the value of the access to the experts that are participating. These are world-leading people in many cases. And when you come to implement a standard, it's very important to be able to understand the intent, because these are documents that have to be created for a large audience. They have to be kept within a certain size. And there's a lot of discussion gone on in the background. So without access to that, sometimes it can be difficult to understand intent. It's also important to understand that in a standard, ambiguity might be deliberate. And that's a tool, a very valuable tool, to help provide an alternative to consensus making. It's very difficult to agree on things sometimes. And if you can leave things a little bit ambiguous, then that can actually help get you over the line and get the standard published and out there and starting to be useful to people. It's also important to remember that the standards are all developed by different committees who are not obliged to necessarily speak to each other or to provide consistency or clarity between them. Very often you'll see that terms are adopted or modified from other standards, but the rest of the terminology in the standard, there's quite a heavy preference to lean on dictionary definitions, but there's 5 different permitted dictionaries for ISO standards, and people don't always check what everything means. So conceptual models can't solve that problem, but they can make it visible. And that's a really powerful tool because it then gives you a sound logical basis for making amendments. So people are reluctant to make changes if they don't see the value in them. And I've found that by creating an ontology of a standard, it provides a very powerful tool for discussion around possible improvements. So we've got two standards, so 26262 and 21434. We've got concepts in those standards, and we're interested in how closely related some of those standards might be. So what I've done is developed a mapping scheme based on SCOS, so that's the Simple Knowledge Organization System, which is a Web3C standard for the semantic web. And extended that with a couple of ideas. So one of the important ideas is an idea of overlap. So SCOS doesn't have an idea of overlap, and it's been noted in the academic literature by a few people that overlap's a really important concept. And we found that actually most of the terminology that we studied fell into an overlapping category. We also introduced the idea of the closeness of a match, whether it was a close match or a broad match. And these Venn diagrams give you an idea of how we understand those different degrees of match. And finally, we need the ability to capture a generic relation between things. But when we do that, it's always important that we specify the nature of the relation so that we've got room for developing the clarity of that relationship in future. So let's take a look at an example of some terms where this might be a useful tool. So in our familiar ISO 15288 system lifecycle processes, we have a term system element, which is a member of a set of elements that constitutes a system. Now in ISO 26262, we don't have the same definition. We have a non-system level element, which has been named a component. So we can see that there's some similarity there. Non-system level sounds like it might be the same as something that constitutes a system. But we introduced this new idea of logically or technically separable. And then in ISO 26262, we make it quite specific by saying that it has to be comprised of hardware or software units. In ISO 21434, they've lent on ISO 26262, as you can see, which came first, and adopted this idea of logically or technically separable, but made it a much broader concept. So we can see that there are clearly some strong overlaps between these concepts, but they're not the same. And it gives you a good illustration of how we could encounter some problems if an engineering activity assumed that the safety engineer's idea of a component was exactly the same thing as the systems engineer idea of a systems element and the security idea of a component. So how do we capture all this? Well, I've developed a simple profile which allows you to understand the terms and the definitions. If you're not familiar with UML, don't worry. This is a class diagram that shows what the ontology elements are that we're going to later turn into our profile. And we have the idea of terms at the top and a special type of term, which is a defined term. And defined terms can have all sorts of relations, as we discussed, to other terms, and they might even conflict with other terms, and so it's useful for us to be able to capture that. And a defined term is composed of a definition, which itself is composed of terms, and also a term, and these terms have roles. So the term is what we use for naming it, and then the definition is what we use for explaining it. So if we combine that with the ideas that we looked at in that Venn diagram, then we can develop a hierarchy of relationships that we can then apply to the relationship mappings between the terminology and definitions in our standards. So in black here are the original SCOS relationships, and in red are the extended relationships. Now, interestingly, this gets a little bit more complicated because actually we can combine these different relationships. So we may have a modified match, which is also understood to be overlapping, but also only slightly similar, so therefore a loose map. So when we zoom out, we get a very big tree of relationships, and the two fragments we've looked at up in the top there, that's the original little ontology that we examined, and that's the diagram on the previous slide, and then all of the combinations drawn out as explicitly named relationships. You don't have to do that if you're implementing this. You could implement rules in your tooling, but that's not necessarily so accessible, and it doesn't necessarily help interoperability because different tools might implement the rules differently. So if you make every single possible legal combination explicit, then that gives you a better opportunity for interoperability. Not everybody wants to work with a SysML tool, and it might not even be the most convenient way or the most effective way of developing these mappings. So what I've done is developed an Excel tool. If anybody's interested in a copy of that, then do let me know. I can make that available offline. And this tool is used to build up the mappings. You can see here some examples where I've got ISO 26262 idea of a component on the left and the ISO 21434 idea of a component on the left. And we've decided, using these drop-down boxes, that there's definitely some sort of match. Actually, it's quite close, but one of the terms is narrower than the other term. And the 21434 term was modified from the 26262 term. So you can capture the relationship either way, but modified by or modified from, depending which is on the left or the right in your spreadsheet. So when we've done that, like I say, it's really important to capture the rationale behind the discussion. So this is really as useful as a tool for discussion about these possible mappings as it is as a basis for integrated modeling. So even if you're not going to build those integrated models, it can be a very useful exercise to have that discussion among your stakeholders about how they understand the terms and definitions and how they might relate. And then the tool here on the right will automatically generate the very specific mapping and provide you with an example definition of the way that relationship should be used. If you bring all that back into a UML model, you can build diagrams like this. So I've got a context boundary for 21434, the cybersecurity standard on the left, and another context boundary for 26262, the functional safety standard on the right. And you can see actually we only end up with some pretty loose relationships between the two. And this is only a fragment of the ontology. I've actually developed much more comprehensive ontologies that capture all of the concepts in 21434 and a lot of the concepts in 26262. Work on 26262 is still ongoing. What you can see is that it's not simple and that there's a lot of scope for misunderstanding. So even by just focusing on these very high level terms and how they might interrelate, you can get a lot of value that you can use to communicate in a single slide that can provide a good basis for avoiding problems down the line when you come to integrating security and safety engineering according to the standards. So with those mappings created, we would hope potentially in future to achieve that value-adding unification, as it's known by INCOSE in the loss-driven systems engineering initiative. In ISO is known as harmonisation. And what we found when we mapped the two standards for cybersecurity and functional safety is that there's actually little direct alignment between the terms, despite the fact that a lot of the terms in 21434 might have been modified from 26262. So the route to harmonisation that we've established is this idea of root terms or common ancestors or supertypes in modelling terms. And we've found that there's quite a good set of core concepts that can be identified. It's not an easy route to harmonisation, though, because then we have to have these discussions about who owns that root term, which working group is responsible for them. We also have the challenge that, well, if we're going to do this for two standards, why not do it for all the standards within a working group's responsibility, or all the standards within a subcommittee's responsibility? Why not do this for everything to do with road vehicles? And that scope creep is quite tempting, but it's also a pretty wicked problem. So we have to be really careful about that. And what it highlights is actually the complexity of these systems that we're dealing with, and the huge modelling and organisational challenges that are involved. But what we're not saying is bury your head in the sand and put this into the too difficult to solve box. What we're saying is, really do some stakeholder analysis, understand what the focus points for your business are, and start small. Choose two standards or two guidelines or two model parts that would be valuable to you, and build mappings between them as a prelude to a larger digital transformation initiative. So the root terms that we found in ISO 26262 21434 study are quite interesting. These were the most powerful linking concepts. So assurance, the idea of an activity, what does it mean to actually do something? What exactly is an architecture? Big focus for systems engineering. We have to understand about how we're going to prove things have been done well, how to check that, so assessment and audit. We've got those system breakdown structure concepts that we've looked at, so component. The idea of a concept here is different to what I've been talking about in functional safety and cybersecurity terms. It's actually more to do with understanding the context and the scope of the technology that you're developing. So a good example of why we have to be careful about the use of terms. Things about the environment, and that's going to become increasingly important, understanding the way that vehicles interact beyond the boundary of the vehicle. And general ideas like, what is the parent concept that security and safety both belong to? So we might have ideas of trustworthiness, resilience, but building on ideas from the NCOSE loss-driven systems engineering initiative, we've identified this idea as a potential source of loss as being really key. Broader ideas like risk and testing and verification are also going to be important. But interestingly, you'll notice some really perhaps obvious terms such as safety, security, and system have not made it onto that list. And that's generally because they've been too hard to pin down and too hard to agree any provisional consensus on. So there's some real value in identifying the missing terms, even if you're not going to be able to harmonize them, because there's such a huge variety in the way that they could be understood. It's useful to have them as a checklist of potential terms that are going to trip you up, even if you can't pin down a definition precisely enough to make it into multiple standards. So doing all this sounds like a lot of work. It is a lot of work, but it's valuable. It helps you separate concerns and keep concerns separate, yet connect across the boundaries between the disciplines. It gives you a simple approach based on proven concepts and techniques. It gives you that prelude for developing transformations between models and model parts, and the basis for that digital transformation initiative. And ultimately, what you're going to achieve through this is greater model richness. And greater model richness is going to pay back in spades through improving your engineering practice and providing better business intelligence. So just in summary, what have I done? What am I suggesting that you do? I focused a lot on context, and I strongly recommend that you use these 6 context setting questions as a tool to help you understand context. You know, whatever you're modeling, whatever you're discussing, make sure that you can answer all of these questions. Listen to stakeholders, and that involves talking to stakeholders, getting outside your bubble, and making sure that the board is on board. Because if your concerns are safety and cybersecurity, then it's difficult, it's expensive, it's resource intensive, and you need that buy-in from the top. Work with other people, work with standards development bodies, work with your suppliers, work with competitors, get involved in developing talent, add value with a transdisciplinary approach, and use model-based systems engineering to help you tame that complexity, and particularly use the techniques that I've talked about today to help you model those multiple contexts and start to bring your various models closer together. Use case studies, keep it small, keep it simple, and use that to demonstrate the value of methods before you go for the big push. And get involved in those standards. Again, I can't overemphasize how useful and important it is to get involved in that standards making activity, because you can influence what happens and you can make it better.